Welcome everybody to MathAA HL. If you happen to be an SL, that's just okay. So what we're going over today is the very beginning of the book, and this section is pretty important. So I think that today let's cover sequences, series, and proofs, or sigma notation. I'm just going to go over sequences and series. So this starts with something which is one of my favorites, which is the co-snowflake. So this is related to my own personal research. So the way you make the co-snowflake is first you take a triangle, and what you do is you have a rule for replacing each edge. So what you do is you chop each edge into, hold on, I've got the wrong thing here. You chop each edge into thirds, and then on each middle third you make a smaller snowflake. Now I'm not doing it to scale here. Okay, this looks pretty terrible. This is an example of what's known as a sequence. So let's go to a new page. A sequence is any list of numbers. Okay. The definition the book uses of a sequence is the same thing, a list of numbers written in a defined order. Okay. Each number in a sequence is called a term. Sequences can be infinite or finite. So an example of a finite sequence might be the number of days in months of the year. So you could have 31, 28, 31, 30, ... That would be a finite sequence ending in 31. You could also have an infinite sequence. For instance, is taking the number 1 and 2 and doubling it over and over and over. So the book has an interesting example of a sequence, and I'm going to have you try this one on your own. For investigation 2, imagine you had a room that was a 5 by 5 square with diagonals. There's 9 diagonals and 5 tiles on each side. If you have another square room that had 13 tiles on the diagonals, then how big would that room be? That's question 1. So I want you to think of that. Pause the video because I'm going to give you the answer. Okay, if you notice, along each diagonal, the length of each diagonal is the length of the room. So the number of squares in the diagonal is the length of the room added together twice. But since there's overlap in the middle, you have to subtract 1. So 13 equals the length of the room twice minus 1. So if we add 1 to the other side to get 14 and divide by 2, we see the length of the room is 7 by 7. How many tiles are needed to completely cover the floor? It would be 49. What if the total number of tiles along the diagonal is 15? Okay. Using the same method, putting 15 here instead, we can just add the 1 over to get 16 divided by 2 to get 8. If there's 135, it's the same thing. We do 135 on this side, add 1 to get 136, and divide to get 68. So 135 plus 1 equals 136. Dividing it by 2, we get 68. Okay, what if it's an even number? Think about it. Can it be an even number? No, it can't be an even number, okay? But if you notice, this gives us a list this gives us 2 sequences of numbers that are associated to each other. You can have the sequence of diagonals, so it's 1, 3, 5, 7, 9. Oops, sorry about that. And below that you can have the sequence of area of the squares you're using. Okay? Okay, so let's talk about a few things that's going on here. How do we write down sequences? Well, a sequence is a lot like a function. So with functions, what do functions do? Functions take a number x and give out f of x. So x goes to f of x, where both of these are real numbers, meaning any number that could be a decimal. On the other hand, in a series, or sequence, we'll talk about series later, we have an, where n is some number, some whole number, and an is what you get out. So n is just any whole number, and an is a real number. It can be any real number. Okay, so what on earth am I talking about? Well, let's take the sequence we had earlier, 1, 3, 5, 7, which is really just a sequence of odd numbers. This is the third element, so this would be written as A3. This is the fifth element, so this would be written as A5. So, what would A1 be? A1 would be 1. A2 would be 3. So, whatever, A is the name of the function or the sequence, and the number 1 or 2 says how far along you go in the chain. Okay, so this book sometimes calls it UN, and it doesn't matter. You can use any symbol up here that you want. So UN or AN is one specific number in the sequence. If you wanted to know all of them, you can put braces UN. This just means a collection. This means the entire sequence. Entire sequence. Oh my goodness. Sequence. Great. Okay. I don't want to talk about series today because they're a little bit more complicated, and since this is our first real lesson, I think I'm going to stop there with the new stuff. So what is your homework going to be like? Well, for the homework, hold on one second. I'm going to want you to pick 2 problems each from problems 1 through 3. And I'll post this online so you don't have to worry about it. So you can stop the video now if you're confident on how to do it. If not, I can show you what to do. So basically, these are kind of like those old things you may have seen on intelligence tests. Complete the sequence. You have to find a pattern that explains the sequence, and you can move on. So for instance, in example 1, if you notice, each one is 5 bigger than the last. So the next 3 terms would be 22, 27, and 32. So how do you write that? Well, this is something we'll use a lot throughout the semester. The first number was 2. And again, you don't have to watch this if you feel confident. And the next one was 2 plus 5. And the next one is 2 plus 2 times 5, because you're adding 5 twice. And the next one is 2 plus 3 times 5. So the way I would write this is that since this is A1, A2, A3, and A4, notice that the number of times we multiply 5 by is always 1 less than the number we're on. This little number is called the index. So the index is n. So the pattern in general is going to be that the nth number, an, is 2 plus 1 minus the index times 5. Now this is complicated, but don't worry. We'll be able to go over this in class. Class time will be spent going over the homework problems. Okay, for the next one, 2, 6, 12, 20. This one's a little more tough. This is 4 larger, this is 6 larger, and this is 8 larger. So the next terms will be 30, because that's 10 larger. 42, because that's 12 larger, and 54. Let's see if we agreed with them. No. 30, 42, and 56, right? Because it's 12 and then 14. Sorry about that. Okay, so this one's going to be a little bit trickier. Because, yeah, we're adding more every time, but it's kind of difficult to find. So one thing we should realize is that you can look at patterns in different ways. That's something a famous mathematician named Euler discovered. So one way to think about it is the first term, 2, is 1 times 2. The second term is 2 times 3. The third term is 3 times 4. The fourth term is 4 times 5. And then 5 times 6. So in general, this is going to be a sub n equals n times n plus 1. Or you could say u sub n equals n times n plus 1. Or you could even use any thing. So you could use ur equals r times r plus 1. It doesn't matter. These are all the different things. Okay, this has been a kind of a long video, but I hope you get the right idea. This example 2 should be a little bit easier. You're just doing backwards. All you have to do is plug in. And then example 3 is just more of finding the general term. So if you have questions about these, please bring these to class. And thank you for coming today, and I'll post the assignment online. Thank you.